welcome back to my YouTube channel, and today we'll be doing the last part of proof by contradiction. So we have 3 proofs left. We were on proof 5, so let's get through them. So proof 6, this is a proof by contradiction. This could be any equation, by the way. This is just like a generic one. Proof by contradiction, 5x plus 15 equals 1 has no integer solutions. So first of all, our negation, assume that there does exist, or that there exists, an integer x satisfying 5x plus 15 equals 1. So what we do is, if we want to show that this is a contradiction, first of all, we can factorize the left hand side. That would be 5x plus 3 is equal to 1. So now this means that 5 lots of something is equal to 1. So we could also just say this: x plus 3 is equal to a fifth, and then like solve for x. So x would be minus 14 over 5. Or we can say that 5 times x plus 3 must equal to a multiple of 5. However, 1 is not a multiple of 5. So here we have our contradiction. So we just say a multiple of 5 cannot equal 1. So contradiction. Then we write our final statement. Therefore, no integer solution exists. Integer solution exists. There we go. Quite a simple proof, easy to see. Okay, next proof, proof 7. So this is a bit different. It's the same concept, but it's a tiny bit different. So proof 7. So now we have a quadratic. Proof by contradiction, x plus 4 x minus 3 equals 28 has no integer solutions. Okay, so first of all, we assume the opposite. So assume that there exists an integer x satisfying x plus 4 x minus 3 equals 28. Okay, so now we just expand to get this simplified. So we have x squared plus x minus 12 equals 28, and then we move everything to one side. So x squared plus x minus 40 is equal to 0. Okay, so now you need to use some knowledge from, like, if you did, if you think about the quadratic formula, what does it mean for something to have integer solutions? So for a quadratic to have integer solutions, its discriminant, b squared minus 4ac, must be a perfect square. Because if you look at the quadratic formula, your a, b, and c are obviously integers. So this will be an integer, this will be an integer. This, however, the only way this can be an integer is if b squared minus 4ac is a perfect square. For example, if I said b squared minus 4 is 49, root 49 is 7, 7 plus this divided by this, you would get an integer solution. So then that's all we have to do. So if I write that down, for this quadratic to have integer solutions, its discriminant must be a perfect square. So b squared minus 4ac would be 1 squared minus 4 lots of 1 times minus 40, which is equal to 161. So now we check, is 161 a perfect square? Well, we know 12 squared is 144, and you know 13 squared is 169, so it's in between them. So 161 is not a perfect square. So we can just say, therefore, 161 is not a perfect square. So the quadratic has no integer solutions. So contradiction. I can just write, therefore, x plus 4, x minus 3 equals 28 has no integer solutions. There we go. Okay, now that was proof 7. Now we are on to our last proof, proving multiples of things. So proof 8, if n squared is a multiple of 3, then n is a multiple of 3. There we go. So now we assume the opposite. Assume that n squared is a multiple of 3, n is not a multiple of 3. Okay, so now first of all, let's say that n, how do you represent something that's not a multiple of 3? Well, you can just say the same thing when you have it's not a multiple of 2. You can just say, like, the first case would be 3k plus 1, because every time you get a multiple of 3, the 3k, you add 1. It's not a multiple of 3 anymore. So if we use this as our first case, we can say n squared, let's just call this n. N squared would be 3k plus 1 squared, which is 9k squared plus 6k plus 1. Then we factorize out the first two terms. Here we see that this is not a multiple of 3. So that's a contradiction because we said it is. We do the same thing. There's another case of 3k plus 2, because let's say you have any multiple of 3, like 99. Obviously 100 isn't a multiple of 3, and 101 isn't a multiple of 3, but obviously if you go 3 more, 102, that is a multiple of 3. So let's do the same thing with 3k plus 2. N squared would be 3k plus 2 squared, which is 9k squared plus 12k plus 4, and we see it's the same thing. We can actually factorize out a 3 from each of these. If we split this into 3 and 1, we would get 3k squared plus 4k plus 1, lots of 1. What's next? Well, this is also the same as this. I'm not going to write it again, but it's the same thing. So we can write, in both cases, n squared is not a multiple of 3. Therefore, our assumption is false. If n squared is a multiple of 3, then n must be a multiple of 3. There we go. So that's it. That's all of our proof by contradictions done. And yeah, thank you guys for watching. I would appreciate if you like and subscribe, and I will see you guys in the next video. Bye.